to a unit impulse will give all the information that is needed for us to find out the response to any arbitrary input. Let us see how we go about it. This is a linear time invariant continuous time system represented as a box like this. Suppose the input is delta t, a unit impulse at the origin, and let the corresponding response h of t is given like this. We also assume in this discussion that if this is a network, it has no initial conditions on the capacitors and inductors, or in other words in a system zero initial storage, zero initial stored energy. The reason is we are going to apply the principle of superposition, and whenever number of excitations are present simultaneously, the responses could be superposed only if the system does not have any initial stored energy, otherwise the superposition principle is violated. Okay. Now, any arbitrary x of t given as an input something like this, this is a general input can always be thought of. Suppose you take a small narrow section of width delta tau, and then let this at the center we will call that tau I, this point tau I, and this section of the input, a narrow section of time, this area can be replaced by an equivalent impulse. So, if you regard this impulse, the impulse will have essentially the same area as this narrow strip, and the area of the narrow strip will be x of tau I times delta tau. So, this will be x tau I delta tau, that is the magnitude of the impulse, and that impulse is situated at t equals tau I. So, provided you make this slices thinner and thinner, then the approximation will be so much more accurate. So, x t can be regarded as approximated as number of impulses. A particular impulse which we have sketched in the figure is x tau I delta tau, that is the area under the curve, that is the magnitude of the impulse, and that impulse is situated at tau I. So, this is the impulse that we are talking about. This section of the input is replaced by an impulse, and several such impulses starting from for the whole duration of the time will be approximately will be equal to x of t. So, x of t can be regarded as summation of several impulses. So, that means your x of t is now being regarded as several impulses like this. So, if we want to find out the response to this arbitrary input, we can find out the response due to the individual impulses and add them up, that will be your total response. And in the limit as delta tau goes to 0, then the response will be faithfully the one that will be obtained when the actual x of t is present. That is the philosophy, that is the strategy that we will adopt. Because we know the impulse response, an impulse at the origin gives rise to h of t. So, any impulse displaced by some amount will also give rise to an impulse response which is displaced by the same amount, translated by the same amount. And by additivity property, if unit impulse gives h of t, an impulse of this magnitude will be this times that h of t. So, that is the principle that we are going to adopt. So, now we now say delta t gives rise to a response h of t. Therefore, any impulse which is displaced by a certain time interval will give rise to h of t minus tau I. What is the principle which sanctions this? This is a time invariant property. Because the network is time invariant, any shift in the input will correspond to the corresponding shift in the response. That is what we had discussed earlier. And instead of an impulse of unit magnitude, suppose you have x tau I delta tau, that is the magnitude of the impulse, delta t minus tau I. If that is the input, you get correspondingly x tau I delta tau h of t minus tau I. So, a shifted impulse will give rise to a shifted impulse response, and impulse magnitude increased by this amount will also give rise to a response which is increased by the same amount. And now here we have a summation of all such things, x tau I delta tau delta t minus tau I, summation as limit delta tau goes to 0, that is your x of t, and that must correspondingly give me limit as delta tau goes to 0 of x tau I delta tau h of t minus tau I, not one such set of responses, number of such responses summed on various ti's, or I will put I summed on various i's. So, in the limit this entire thing goes to x of t. So, as you make delta t goes to 0, all these impulses is equivalent to the input x t as we have seen. From x t we have generated these impulses. You make them closer and closer, approximately that will be the same as your x of t. So, x of t is regarded as a series of impulses, and correspondingly this will now be, you have a number of these things, well delta t, that is why it is an integration of x tau h t minus tau. So, tau I is not discrete points, it continuously it exists, delta t d tau, that is your y of t. So, y of t is obtained as x tau h t minus tau d tau, that is how we can obtain in the limit the output y t corresponding to this x of t. And in general, the most general case, this integration must last from minus infinity to plus infinity, but in the more usual cases the limits can be further restricted, as we will see at a later point of time. So, in other words, given any input x t, the output can be obtained as x tau h t minus tau integrated between minus infinity to plus infinity. This is a function of time. Tau is the variable of integration that gets cancelled out, final result will be a function of time. So, this t stays, and that is your y of t. And this particular type of formulation is usually represented as h t x t starred h t. This is referred to as convolution integral. So, if you convolve two functions of time x t and h of t, the meaning is this particular integration x tau h t minus tau d tau. So, let me rewrite this. We will come back to the impulse response and the calculation of y of t, but let us spend a few minutes on the meaning of convolution integral. So, convolution integral of two quantities f t, convolution of f t and g t represented in this manner is f of tau g of t minus tau d tau. This is a symmetrical arrangement. We can also write this as g tau f of t minus tau d tau. As I said, normally the integration is minus infinity to plus infinity. This is called the convolution integral, sometimes called Faltung integral. That is, the German name is Faltung integral. So, what is involved in this integration? It is instructive to see physically how we interpret this integration, this convolution principle. So, let me illustrate this by means of this picture here. You have two time functions f of t and g of t. You would like to find the convolution of these two. What you do is you keep one of these f t fixed. So, let us say this is f t, this is fixed, and this g of t, suppose you reverse this, the time axis, that means g of t is like this. This what you are having here is g of minus t, this is g of minus t, that means you fold it, g of t is folded along the y axis. So, the sequence of values which it takes for positive t will now take for negative t and vice versa. So, you fold it along the y axis, this is g of minus t, and then suppose you want to find out the convolution integral for a particular value, say t1, then this g of minus t you advance it in the forward direction by an amount equal to T1. That means this is g of minus t, you advance it by an amount T1, this becomes g of minus of t minus T1, that is g of T1 minus t. That means you shift it, that you are having this. Now we have the product of, in this convolution here, f tau g t minus tau. Therefore what you are doing now is this original f of x that you are having, or f of tau that you are having, and this shifted g of t, you multiply them out, and this will be your result. The product of these two functions will be this, and you take the area under that curve, that is the integration, that will give the convolution value at t equals T1. In other words, what we are doing is you take original one time function, keep one time function as it is, the other time function you fold it, then shift it by the required amount, then multiply, then take the area under the curve, that is integrate. So the key words are fold, shift, multiply and integrate. These are the four words, the key words that are involved here. This will be explained a little clearly, more clearly perhaps, by taking this particular thing. Suppose this is f of t and then you are having a g of t here. This is g of t is the triangular curve. So what we are doing now is, instead of having like this g of t, you shift it, you fold it like this. So g of t originally was like this, now you folded it, that means you made this run backwards. This is now g of minus t. Now depending upon the point where you want to find the convolution, you shift it like this. So for various shifts you find out the product of these two curves and find out the area under that curve, and this is how one can calculate the convolution values, integral values for elementary time products. So the key words here are fold, shift, multiply and integrate. So you are having here f, g of t is the time function, g of minus t is what is obtained by folding, shift it, so g of t minus tau, you shift it by the amount at which you want to calculate the integral. At t equals T1, if it is you want to find out the product of this at T1, you fold it, you shift it by that amount T1. In a general t, g of t minus T1. Multiply, so f tau is multiplied by g of t minus tau, and then integrate, that means you find out the area under this curve. So these are the steps that are involved. If you keep this at the back of your mind, we can find out the convolution of simple functions quite easily without going to the mathematics. From physical graphical approach, you can find out the convolution of different functions very easily.